Professor Ronald Cornet. Ronald is a professor at the Amsterdam University Medical Center in Medical Informatics. And the topic of today's presentation is Biomedical Ontologies. As a reminder, this series of lectures is an introduction to several topics around the FAIR principles, and it's important to attend if you are attending the training school that we are organizing again together with HemaFair and Helios at the beginning of May this year in Cyprus. So, Ronald, thank you very much. The floor is yours.
Okay, thank you very much for the introduction, and thank you very much for the opportunity to present this third lecture on biomedical ontologies. So I'm Ronald Cornet. I'm a professor in medical informatics at Amsterdam University Medical Center. And as a group, we are participating in the HemaFair project. So this is part of our contributions to provide training on fair research, fair data, and the FAIR principles, and everything pertaining to that to, well, participants of HemaFair, to participants in the Helios cost action, and more broadly to anyone interested. So I'm very happy to see that we have a good turnout this afternoon. So, well, ontologies, I realize that it's often a word that may confuse people. So before diving into ontologies, I thought it's good to provide a few examples where many of them also, well, contain the word ontology in their name, but not always. And there's many ways you can, well, look at ontologies. So ORDO, the Orphanet Rare Disease Ontology, is one probably well known, especially in the area of rare diseases. There's the Human Phenotype Ontology, the Basic Formal Ontology, BAFO, Gene Ontology, but there's also systems like SNOMED-CT, which used to be an abbreviation for systematized nomenclature. So SNOMED-CT never called itself an ontology. And well, actually, there can be, well, heavy and hefty debates on when something can be considered an ontology, but well, I prefer not to go there and rather say, okay, sometimes they're called ontologies, sometimes nomenclatures, vocabularies, thesauri, terminologies, well, largely different words for very often similar things. And well, mentioning only 5 here, it's good to acknowledge that if we look into BioPortal, that, well, at this moment, there's, well, close to 1,200 ontologies being included, spanning in total over 15 million classes. So ontologies in the field of biomedicine is definitely an important domain, and there's a lot of work happening, developing them, applying them. I think that should definitely be increased and improved, and researching them. So, well, if we look at ontologies and their use, I basically well, see the 3 main purposes of ontologies as encoding, describing, and ordering. And in this presentation, I would like to go through these 3 purposes and then look at some examples. And if time permits, I would also address a little bit on schemas, yet another word, because that closely relates to ontologies. So if we look at encoding, when we look in patient records, we, especially traditionally, when records were fully free text, we would come across utterances like these: some Mr. John Doe with a date, an RR, which is a Rivarocci blood pressure, 120/80, BMI, probably body mass index of 29, and OI. In this case, in my example, which I see as a diagnosis of osteogenesis imperfecta. So as humans, we are often quite capable of determining or inferring the meaning of the elements of such an utterance. But if we really want to be able to work with data like these in a machine processable fashion, it is good to make sure that the information is as much as possible disambiguated and represented in such a way that it has basically a unique meaning and for man and machine, a single understanding of what is represented. So the first step for that is basically to determine what are the things about. So the thing hidden in this representation was the actual attributes like name, gender, date of birth. So we had to infer that John Doe is a name, that Mr. refers to the male identity, etc. So when working towards structured and standardized representation of information, the first step is to make those attributes explicit. And actually that already refers to the schema that I will address later. So we will get back to this example. So as said, on the left hand, we see the attributes, the properties, as you will, of a person. And on the right hand, we see the values, which are basically the only parts represented in the free text. And these values can be of various types. We see a string, like the name. We see a date, like date of birth. And we see numbers, like 120, 80, and 29 for the body mass index. And then we see the things in green, which are the so-called categorical items, like male identity, where we could also have female identity, millimeters mercury, where we could have other units like maybe hectopascals or liters, not for blood pressure, of course, and types of diagnoses like osteogenesis imperfecta. And for all of these categorical items, be it values, be it units, ontologies come in play. So what we can do is add basically unique codes coming from ontologies to uniquely identify each of these items. Because like date of birth, as long as it's English, many or most of us will understand what that means. But if I would have represented date of birth in, say, Finnish, I'm quite sure that most of us would not have understood, including myself probably, what that exact data element meant. And this is overcome by using codes. And in this case, I suggest to use LOINC codes, one of these coding systems, ontologies, if you will, for coding observable entities, as they are called, or if you will, attributes. So we can encode date of birth through LOINC code 21112-8. And in the similar way, we can provide codes for each of these elements, and we can provide codes for the categorical values and units. So for male identity, we can pick a SNOMED code where we see a lengthy number, 44, etc., ending with 109. And this code uniquely identifies male identity according to the SNOMED coding scheme. For units, we can use UCOM, Unified Codes for Unit of Measure, where it is represented as millimeters and then mercury between the square brackets, Hg. And osteogenesis imperfecta can be encoded using the ORFA codes, in which case it is ORFA code 666. So what we see is that we, in this way, can basically transform a free text description to a structured, with all the attributes, and standardized through the use of all these ontologies representation. So what we encode, or if you will, what we identify, are data elements, such as blood pressure or date of birth, and categorical data values and units, such as male identity, millimeters mercury, and osteogenesis imperfecta. And this helps prevent ambiguity because whereas for OI or for RR, the question may be, what does it exactly mean? I have had people bring up, but RR isn't that respiratory rate? Well, in another context, it could have been that. So by encoding, we disambiguate and we make the meaning of each of these data elements and their values clear. So that is the first use of ontologies. And the second use is providing descriptions. And basically providing descriptions for humans and for machines. And to distinguish them, for the humans, I refer to things in the blue font and machines in the red font. So for humans, ontologies include descriptions in multiple languages, provide synonyms, etc. So where I said date of birth could be represented in English, in Finnish, in Dutch, etc. This is dealt with by ontologies. And as we see on the right-hand side, OrphaNet provides labels for the items in many different languages. Well, Finnish isn't among them, but there's quite a few others. And it also provides synonyms. So if we look here at the example of osteogenesis imperfecta, we see the abbreviation OI, we see Poracan-Durante disease, brittle bone disease, glass bone disease, all as synonyms for the same disease concept, OI. And we see some further description like prevalence, inheritance, and age of onset. So all of this is useful information for humans because, well, we as humans wouldn't understand ORFA 666. So we need such descriptions, human language, natural language descriptions to be able to, well, interpret and understand what this code or what this concept means. Trying to get to the next. Yeah. Oh. So looking at the machine description, it does not only provide the descriptions by the labels that we understand, but one example of machine descriptions is shown at the right, where we see there is a lot of alternative descriptions of ORFA code 666. There's a whole set of OMIM codes, which are all the blue ones that we see underlined. And there are identifiers in UMLS, in MESH, in GUARD, and in MEDRA. So each of these different systems provides codes to describe osteogenesis imperfecta. And for a machine, this is important to have this information, because then if a system hasn't used like ORFA codes, but for example, ICD-10, then a machine will be able to interpret that actually ICD-10 code Q78.0 is a different representation of the same concept, osteogenesis imperfecta. But there's more, because for machines, there is also a description of properties. And here I show an example coming from SNOMED CT, where we see, apart from an identifier and a whole set of English language descriptions of the concept, we see a specification of the properties of osteogenesis imperfecta, like the finding site, which is a bone structure, the occurrence of disease, which is congenital, the associated morphology being dysplasia, and the pathological process being a pathological developmental process. And in terms of its interpretation, it basically interprets as an abnormal bone formation function. And this description, this use of properties is important because machines can then use these properties for further inference. For example, if we would be interested in all diseases in SNOMED CT in this example, which occur congenitally, we could look for diseases which have this property occurrence being congenital. And we can query for all these diseases. And we could search for all dysplasias, and we could do combinations and say, okay, we're interested in all congenital dysplasias. And we would then, as an answer from a machine, get osteogenesis imperfecta and other diseases. So the second purpose of these ontologies is providing such a description. And the third purpose is to provide ordering. And the ordering has two purposes, basically for input and for retrieval. If we look at input, it's important that we can record data at a varying level of detail, because sometimes you may not know the exact type of, well, in this case, osteogenesis imperfecta. And a clinician might want to capture that the patient has OI. But maybe further research has been done, and it has been shown that it was OI type 5. And then a clinician would want to be able to record that the patient suffers from osteogenesis imperfecta type 5. And you also want to know that osteogenesis type 5 is actually a type of osteogenesis imperfecta. And well, in this specific example, it may sound trivial, but there is plenty of situations in which it may not be exactly clear which diseases are subtypes of which other types. And this hierarchical ordering, so on the one hand, supports the recording at a varying level of detail, but it also enables to retrieve at varying level of detail. So I could query for all patients with osteogenesis imperfecta type 5, and then I would, of course, get those patients who have been recorded as such. But if I would query for patients who having osteogenesis imperfecta, I would like to get not only patients which had in their record osteogenesis imperfecta, but also type 1, 2, 3, 4, and 5. So I want to be able to capture in the detail that I have clinically, like type 5, while retrieving at a coarser level of granularity. Or I could even say, I want all patients with a type of rare bone disease. And then if I search for like rare genetic bone disease or rare bone development disorder or rare bone disease, as we see it here, we see that in all of these cases, osteogenesis imperfecta is a type of, well, rare bone disease. So if I would query that, I would get all patients having osteogenesis imperfecta, probably also a whole set of other diseases, and also all subtypes of osteogenesis imperfecta, 1, 2, 3, 4, and 5. So these are, I think, the important purposes of ontologies. And I'd like to stress that the importance is that when capturing the data, you don't really need to do anything with that. Sometimes people, I've got people asking, so do I need to specify all of that every time I capture information for a patient? And then the thing is that it's important to realize that actually you can simply state that a patient, John Doe, has a diagnosis of osteogenesis imperfecta with a system that helps to capture the information in a proper way. And then I can add the ontologic knowledge to it. So I can say John Doe, and this is in a formal specification. I refer to RDF and RDFS, and maybe we'll get to that in another lecture, so you may forget that for now. So basically what I say is John Doe is a Homo sapiens, a human, and by that you get for free that this John Doe is actually a primate, is a mammal, and is a vertebrate, and many other things, which we, I think, in providing healthcare rarely care about, or we just take for granted that every patient that comes into into our room is a primate. But this information is, well, ontologically provided by a system like UMLS, for example, the Unified Medical Language System. And the same goes for osteogenesis imperfecta, where we say, okay, that is an instance of the concept osteogenesis imperfecta in some ontology. And I get all the information, such as the fact that it's a primary bone dysplasia and that it's a rare bone disease. I get all that information for free, if you will, from the ontology. So to summarize the ontologies part, they serve three main purposes: encoding to provide unique identifiers, that is a unique identifier per ontology. And if there are multiple ontologies, we saw that there can be multiple identifiers which are then mapped to represent entity types like concepts, like data elements and properties. The describing is both for human readable labels like names and synonyms in, well, many languages, and the provision of machine readable properties and mappings to other descriptions across ontologies. And the ordering helps storage and retrieval at arbitrary level of detail. So I would like to show a few examples based on Wikipedia and Wikidata. I think all of us know Wikipedia, where humans can find information about concepts. So here, if I hover, we see this actually links to Wikipedia, the rare disease page. So this will provide a description of rare diseases. So if I click that one, we see how we know Wikipedia as a description of what a rare disease exactly is. But it's important to realize that behind Wikipedia is Wikidata, which is a stricter representation of the same information. And the good thing is that it's not only such a representation, and I will show an example shortly, but we can also query over those data. So, for example, if we look at the Wikidata page on osteogenesis imperfecta, we see, and it's basically what I showed in the beginning on the patient record, where it says John Doe with some date of birth, that we have to infer that it's a date of birth. Here we see in Wikidata the structured and standardized representation of OI. So we see descriptions in various languages, and we see all kinds of statements. It's an instance of a rare disease. It is a subclass of osteochondrodysplasia. We see an image of OI. We see the relevant specialty, in this case, genetics, a genetic association, etc., etc. ICD-9 CM code, well, and this goes on for quite a while. So here we see all different kind of information in a structured and standardized way about OI. And that's nice, because in this way, through this structured and standardized way, we can query. And for example, I can query for rare diseases. And basically here, this query, and forget about the query language. This is just an example. We can always dive deeper if you're interested. This is called Sparkle. You can query for, in this case, all diseases, which is an instance of, let's see if this wants to hover, which is an instance of a rare disease. So if I query this, and this is great for machine readability, all identifiers, but not very useful for us humans because, well, none of us, I think, knows by heart what Q1485 is. Fortunately, I think I can click it and it gets me to SLE. So this shows how we can do the machine processing of information in Wikidata, if you will, in Wikipedia. And we can go beyond that. We can show, well, for example, the names with the rare diseases, which is convenient because, as we saw, well, just learning all those labels by heart or all those codes, that's not something we would want. So then we see, well, some syndromes, Anderson-Tawil, Dennis-Dresch, etc., Dresch, sorry, etc. And we see that in Wikidata there is almost 3,600 rare diseases. So in this way, and I'll skip the last example for the sake of time, but the links are on Zenodo actually, so there you can, I think, also find the link. We can see, for example, people who died of a rare disease, or the number of people in Wikidata who died of a rare disease. So all this kind of querying we can do based on the machine representation in which information is structured and standardized using ontologies. Using ontologies and schemas, because, and it might be that some of you, or maybe even many of you, have already seen this. Here is a little schema, if you will, the set of common data elements for rare diseases registration. This was developed through the EU, and it provides the basic data elements that would need to be described for individuals, like a pseudonym, date of birth, sex, the patient status, date of death, if any. And what this basically provides is a short description of the attributes, the parameters, the variables, whatever you would want to call them, that are to be captured for rare disease cases. And such descriptions of required or requested attributes, parameters, that is what's called a schema. And in these schemas, well, there's quite a few ways to specify those schemas. So we saw this one from the Joint Research Council from the EU, which was largely a textual description presented in a PDF. In healthcare, there is also a standard, and one of the coming lectures will dive deeper into HL7 FHIR. This provides a description, for example, on the right-hand side of a schema for conditions. So what do we describe for, well, diseases, if you will, or generically for conditions? Like a clinical status, a verification status, a severity, a body site. And of course, we would need to look into the exact meaning of all these parameters, but that is beyond the scope of this lecture. But what we see is that it provides a list of such attributes for describing a patient's condition, that it describes if it is the so-called cardinality, if it is mandatory. If we see a 0, it means it's optional. If it starts with a 1, it means it's mandatory. And the cardinality showing if it can be at most 1 or at most any, basically larger than 1. So this cardinality describes, well, if a parameter can basically repeat for a condition. And we see the type of allowed values. And we see sometimes these are numbers like identifiers or a date time. And we see many codable concepts, which basically means values coming from some ontology. And this is HL7 FHIR, but there's also OMOP, CDM, and also for this, we will have a follow-up lecture diving into the details of OMOP CDM, what it is, when to use it, how it relates to HL7 FHIR, etc. And there we see that for a condition, we describe the person ID, a concept ID, a start date, maybe a start date time, an end date, and maybe an end date time, if we know exactly the time that something started or ended. So we see that there are commonalities among OMOP and HL7 fire. Then a different example, blood pressure, because this is like a prototypical example of such a schema, or as it's called here, an archetype. The information we can capture for a blood pressure. And we showed like 120/80, so which is the systolic and the diastolic pressure. But we could also capture things like the location of a measurement. Was it left arm, left leg, right leg? What was the cuff size that was being used? Was the patient sitting, standing, lying down? If the patient was lying down, was the patient tilted? Was the patient at rest or exerting, etc., etc. So this is a schema, also called the detailed clinical model or clinical information model, that provides all the possibly relevant information for a blood pressure coming from open air. And then one more, and this is the last one, well, I say many others, pheno packets, a standard that has a focus on bioinformation, focusing on phenotypes. And also here we see that when describing a disease can have a term, which is basically the type of disease represented through some ontology. A disease can have an onset, can have a date that it was solved, the resolution date, which is some point in time. It can have a stage. If it's a tumor, it can have a TNM staging. It can have a primary site. It can have a laterality. And we see a whole bunch of these are represented using ontology classes. So this is how ontologies and schemas interrelate. So these schemas aim to describe the properties of classes, like properties of a condition, properties of maybe a person, properties of a blood pressure measurement even. And they aim to characterize those properties by cardinality that I showed, like is it one or multiple? The optionality, is it mandatory or is it optional? And the type of allowed values, like is it a class from an ontology, is it an integer, or is it a date? So, and in this way, schemas and ontologies come together, and we see here a small schema for a person, where we say schema has a person has name, gender, etc. Name is exactly one string, and this is a, well, kind of crappy representation. I can say that because it's mine. Patient can have a gender, which is exactly one SNOMED coded gender identity finding. Date of birth is exactly one date. Well, blood pressures can, of course, be multiple. So one or maybe even zero or more diastolic, systolic values. Body mass index, well, at any point in time, it will be one. And diagnoses, which can be one or more ORFA codes, for example. Or maybe we allow for other ontologies as well. That is what the schema will then describe. So ideally, and unfortunately in practice that's not yet the case, schemas identify their elements and the allowed values using third-party ontologies. So like I was referring to LOINC and referring to SNOMED in my schema, well, although the representation might be crappy, I at least adhered to adopting third-party ontologies like LOINC and SNOMED for the representation. But in practice, these schemas are provided and then mappings are added. And sometimes it's quite clear how then the elements relate to certain ontologies, and sometimes they don't. And in the same way, mappings are defined among schemas so that we can, for example, interpret HL7 fire information and represent it in such a way that it fits with OMOP CDM or with phenopackets. So to conclude, ontologies, they aim to encode, describe, and order concepts in hierarchy, and schemas aim to describe the relevant properties of classes and to characterize the properties along cardinality, optionality, and allowed values. And with that, I'd like to conclude. Here's my information. If you'd like to follow up, I want to thank you very much for your attention. Please find again the link for the survey. Please take it if you haven't done it already, the survey on data protection and consent. And now I'd like to open the floor for answering any questions. Thank you so much.
Thank you, Ronald. Very nice presentation. So are there any questions? Or maybe I can start. I see a question by Theo. So please, Theo.
No, please
yourself.
Go on. That's right. If you wish, please go on.
No, please ask,
Right.
and I will ask later.
Yeah. Of course, this a special course group where there are physicians perhaps and things like that, but there are a lot of cases I see in other course actions where researchers develop their own data sets, their own research, and they may struggle to find the way to bridge or to merge their, let's say, developments, the attributes with, for example, we work in a digital biobank with physical activity with a cost action. And there you have, let's say, some lifestyle data, which is less formalized issues. How do you, let's say, ensure that you are going to develop a strategy for FAIR on the one hand, and your results can your let's say work in the future may have let's say could be without any problems. I'm not sure if you get my main point. You have unique, less formalized, let's say, fields, attributes, and what do you do in that case?
Yeah, thank you for that question. It's really an excellent question, and something that does occur in practice. I think you mentioned lifestyle as an example, and I think that's definitely a domain that needs further further work on. We in a previous research we had things like sports and hobbies, and also there found that it is quite hard to find systems, ontologies, if you will, that can be used to represent that information. So I think my answer will be multiple. So the first thing is indeed the question, is this indeed an area for which there are no ontologies? Because
there are ontologies in
Yeah.
some lifestyles and things like
Yeah.
that, but you come up with some unique. You as a researcher, you wish to explore, let's say, this kind of and lifestyle is, or in physical activity also. Okay, you can count the steps. Okay, you have a schema for that, but what else?
So I'm not saying that there are no ontologies. I fully agree that in this case it's the case. I see too many people reinventing things that are already there. So the first step is make sure that this is indeed a problem. And I would agree that in domains like these, it may definitely be the case that we need more. There are no properly usable ontologies. And then I think I think that definitely one of the things that we need to explore and address also within HEMAFAIR and similar projects is to I always say don't create ontologies, but sometimes you may have to because there is nothing else. And then I think it's important to start with at least lightweight ontologies where we capture like if I take sports as an example, where we take the sports that are in context, we include them in a system that we can share. So in an ontology, which we make available through, GitHub or whatever repository.
There is the physical activity ontology, Paco, so there is something over there already.
Okay.
But yeah, there you are always coming up with some new things. Sorry to interrupt.
So I think if there is something you can build up, or build onto, you can create an extension of such an ontology and add to it, and basically say, okay, we include the ontology that exists, but we build on it. And well, like I said, I think the best there is to make sure that whatever you create, you make it available as properly as possible as a machine readable resource. So in one of the previous lectures, Martijn Kersloot gave an introduction on the FAIR principles. And well, while we talk a lot about FAIR data, basically the principles say it's not just the data being fair, but it's also the systems and ontologies that the data is built on are also fair. So that would mean that we create, and maybe as simple as it is, an ontology, but make sure that we can share it, like I said, for example, through GitHub, and maybe be able to create a small community of people who are willing and able to maintain, to add some concepts, or maybe later on to add some hierarchical or some hierarchies if there is a need and a possibility for that. So because I fully understand, we can't say, oh, we want to do something and first we need to do ontology engineering for the next 4 years before we can continue, because you cannot wait for that. So like I said, I think it will be good. I don't know, I haven't seen them. If there would be some guidelines for, let's say, lightweight ontology development in such a way that we can scale it up over time. And I think that's really something that can be done. And
there are some tools, but the thing is, who is going to validate and who is going, let's say, I don't know if you are aware, is there a repository of all these different, let's say, we have Wikipedia, we have, let's say, but is something that where you can definitely you can search to establish ontologies if there is already something that is close to your attributes, to your fields.
But, so
yeah.
One thing I should add there, I think, is if there is something that is already close, I think the first thing is to reach out to whoever has developed the existing systems and to seek collaboration on expanding them and on including the requested or required content in there. Because I think in the earlier days, one of the criticisms for ontologies was always, yeah, it has a lot of what I need, but it doesn't have everything, so I'll make my own from scratch. And I think in these days, well, like I said, there are 1,200 ontologies in BioPortal. We need to seek collaboration, and we need to check what's out there and collaborate. And the thing is, whether you build your own or whether you build on or contribute to an existing ontology, I think we always need ourselves to organize the reviewing and the quality control. I mean, there's no one who sits at home waiting for someone to ask, hey, can you check my ontology? So whoever is establishing something like that will need to work on that and will need to organize the governance of such systems themselves.
Yeah, and this, I'm sorry, Stefania, just to say a word, I found it very recently, it is quite useful for all the scientific community. There is the data sharing playbook up by the University of Trinity in Dublin, if I remember well. We need to find ways, and all things goes to unification, let's say, to have, let's say, some common standards, some common, let's say, approaches. Yeah, wonderful. Thank you.
Thank you for the question. And I think so. Was it that I see quickly looking the data protection handbook from Trinity College?
Yes. Coralia, would you like to ask your question?
Yes. So thank you, Ronald, for this. I really enjoyed this presentation, to be honest. Personally, I used in my line of work EBI ontology lookup service and bioportal, which you have shown in your presentation. So by saying this, we use different types of ontologies. For example, one being the sickle cell disease ontology is disease specific. So maybe I'm rushing this. I should wait for the next talk, but since everything is linked together, Fire 7, you presented it as a, I will call it tool for sharing data. So this Fire 7 system, does it accept different ontologies like codes, or is it already formatted to use specific ontologies?
Okay, good question again. Fire, so HL7 Fire, and well, I will not do all the details. That's indeed the other talk. It is open, so it does allow. So what I showed the example of conditions where it says codable concept, and codable concept basically means it should come from any system. And the system can be like SNOMED, the system can be Ordo, but the system could also be the sickle cell disease ontology. So HL7 Fire is very permissive. But then if you well want to specify details in a given community, then you can be more restrictive and, for example, say, well, in this case, for this piece of information, we would want you to use the sickle cell disease ontology. But the principle is Fire is permissive. So you can, as a starting point, you can pick that ontology that works best for your situation.
Thank you. That this comment clarifies a lot. Thank you so much.
Good. So, and we'll continue that in the Fire presentation.
Thank you.
Thank you, Coralia. So I have a question as well. So, in real case scenarios, we may have like a long list of parameters that we need to standardize and choose for each one the right term to align with our variables. So I'm wondering if there is a role for artificial intelligence in this process, and whether there are any tools that can facilitate the standardization of non-standard CRFs, let's say, whether you can just, specify an LLM, or there are already some LLMs that can be used for medical informatics and for this kind of applications.
That is actually an area where there's quite a lot of work going on currently, and it's also one of the areas that we really want to contribute to, because it is quite a lot of work, especially if you have existing data sets that you want to like map to existing ontologies, then it can be quite an effort. Well, AI and large language models can definitely be of help there. But I think the current status is, well, we're getting started. There are some good results here and there, but well, doing it adequately is currently, well, also with AI, a challenge, because you first have to, well, basically determine what the proper AI is that can do it for you. But like I say, there is a lot of work going on, so I'm really optimistic that over time this task will get, well, at least a bit easier.
Okay, thank you. Are there any other questions?
The slides become available correctly, because I would like to try that wiki survey thing on my own time.
I will check. I will go to slide 1 again. I didn't, maybe should have added the reference here. Maybe I kill my PowerPoint now. Well, the slides, they are on Zenodo already, and if the link, I'll check if the links are working, and otherwise I'll update that. Yeah, and feel free to reach out to me so we can get that going.
Thank you. So we are almost out of time. So thank you very much, Ronald, for this very interesting presentation. And thanks to everyone for attending. Our next presentation of this series is on the 27th of January. Same time, it will be on conceptual models that are used in medical informatics. So I hope I will see you again in the next lecture. Thank you very much for joining.
Yes.
Thank you.
Thanks all.
Bye.
Bye, everyone.
Thank you. Bye-bye.
Thanks a lot. Bye.